Under 3.7, we are going to talk about region and say the following. You can use shading on graph to identify regions that satisfy linear and quadratic inequalities. When you want to show the region when y is less than the function of x, this is the region that is of course below the line, because the value of y is below the line, below or rather the curve. Yeah, it's a curve. It could be a line. Y is equals to fx could be a line or a curve. So when the region is below the line or the curve, then it represents y or values of y which are less than the function of x, or below the line or the curve. But when y is above, y is greater than fx, that region is the region above the line or the curve, which is represented by the graph y is equals to fx. We could demonstrate this in a graph or in a curve, something like that. And this is the graph of y is equals to fx. And you can see for all the values of y in the shaded region, for all the values of y, if we could name this region, we are going to name it and call it y is greater than the function of x, because that region is above the curve. If we could shade this region with a different color, probably red, then we could say that all values of y in the red shaded region are less than the function of x. What do we mean by that? If we could take this particular point, which is in shaded black, the value of y here is far above the value of y on the straight line. And that is why we are saying y is greater than fx. If we could take a particular point like this one, which is in the region which is shaded red, the value of y there is far below than the value of y on the straight line. That is why this region satisfies the inequality where all y's are less than the value of y given by the function. And this one takes us to direct to example 13. And let us see what happens in example 13. Let us see what happens in example 13. Above on page 52, we are told, before we study example 13, we need to understand that if y is greater than fx or y is less than fx, then it follows that the curve y is equals to fx is not included. It is not included in this particular, because you can see y is just greater than. There is no that aspect of equals to. Y is less than. There is no that aspect of equals to fx. And that is why along the line, along the curve, y is equals to fx, it is not included. All the values of y along the curve or along the line, they are not included. But you can see when y is greater than or equals to, or y is less than or equals to the function of x, then you can already see that the values of y is equal to fx, all of them are is included. All the values of y along the curve or along the straight line, they are included because of the aspect of the equals to. Sometimes when we talking about greater than or less than, we talk about the broken line, something like that. But when we have equality, then we talk about continuous line. We're going to see in our example 13. Example 13 says, on graph paper, shade the region that satisfy the inequalities, which is one inequality is y is greater than or equals to -4. Another inequality is x is less than 5. Another inequality is y is less than or equals to 3x plus 2. And the last inequality is x is greater than 0. What we need to understand is all these inequalities, we are first of all supposed to treat them like equations. So that we can exactly note where the boundaries are. And the equation generated by this inequality is y is equals to -4, x is equals to 5, y is equals to 3x plus 2, and x is equals to 0. The reason why we have done that is actually to note or to quickly highlight where our boundaries will be. So the line y is equals to -4 is not anything that we can struggle to understand. The line y is equals to -4. We can talk about it here. This is -4. We could have -3, -1. Y is equals to -4. We need to come up and see what is the nature of our inequality. Is the line continuous? Is the line broken? And fair enough, our line is continuous. So this is the line y is equals to 4, and it is the boundary. But we need all the values of y's. We need all the values of y's which are greater than -4. Greater than -4. So if we take 0, and because 0 is above the -4, is 0 making sense? So 0. Is 0 greater than -4? Yes, it is in the wanted region. It is actually in the wanted region. So naturally, we should shade the unwanted region that way. And we are through with that. Let's go to x is equals to 5. 1, 2, 3, 4, 5. X is equals to 5. Is the line broken or continuous? Broken. So we should have something like this. But always name the line. We need all the values when x is less than 5. Of course, it goes without saying. If we take x to be 0, 0 is less than 5, and 0 happens to be in the wanted region, so we shade the unwanted region again. We shade the unwanted region. Let's first of all deal with x is equals to 0, because x should be greater than 0. We are talking about x being greater than 0. Fine. If of course this is the line x is equals to 0, and because we are talking about x being greater than 0 as another boundary, all values of x. No, this is not x is equals to 0. This is y is equals to 0. We are talking about x is equals to 0. Please make that correction. X being greater than 0, if we go to the left, we are going to have -1, -2. Of course, those are not greater than 0. But because we want all the values of x greater than 0, then we can talk about 1, 2, 3, 4. All these values from 1 to moving forward, all the positive value here makes sense because 1 is greater than 0. So again, we shade the unwanted region. Again, we shade the unwanted region. At that particular point, we need now to evaluate what we can do with y is equals 3x plus 2. And this one we just need to tabulate, make the value of x and y. When x is 0, y is obviously 2. When x is let's say 2, y is 6 plus 2, which is 8. All right? When x is probably, let's talk about -1, then we are talking about -3 plus 2, which is a -1. When x is -1, -1. When x is 0, 2. When x is 2, a very big number like 8 there. So we are going to talk about a straight line that is going to be that way. We are supposed to do this on a graph paper, but this is the line. We can name this line, we can give this line a name of y is equals to 3x plus 2. Now, at that point, we need to examine points above the line and below the line. Remember, we need the value of y, which is less than 3x plus 2. We can go to point 0, 0, the origin. At this particular point, y is 0. When y is 0, x is also 0. So let us see whether it makes sense. So 0 is less than 0 plus 2. So at 0, 0, 0 is less than 2. Does it make sense? Of course it does. It does make a lot of sense. So that could be our wanted region. But let's see, let's go to point like this one, which could be 0, 4. At this particular point, x is 0 and y is 4. Let us substitute 4 there. Is less than or equals to 0 plus 2. Y is 4. 4 is less than or equals to 0 because x is 0 plus 2. Does this make sense? No, this one doesn't make sense. So it is already in the unwanted region. So we shade the unwanted region, and what we are left with is the region that satisfies all these inequalities. We are left with the region that satisfies all these inequalities. This is not new. We have done that this in year 11, and I think nobody is going to get lost, and that is why I don't emphasize so much on exactly what you're supposed to be doing. But yes, inequalities, first of all, they should be treated like equations, and of course examine the resulting points, whether they make sense or they satisfy the inequalities or not. Okay.